you can see National 5, you can see Higher, you should be able to see Advanced Higher, and you should also be able to see Advanced Higher Experiments. Right, okay, so the bing bong's just gone off, so that means it's recording. So everybody who's not here is going to come back to this later. I've sent a link in an announcement on Classroom this morning about how to get to see a couple of things using a package called Virtual Flash. Actually made a few years ago by a former physics teacher in Fortrose. There were two Mr. Sharkeys. I don't know if you won't remember Mr. Sharkey, I don't think. Probably before your time. There was Mr. Sharkey Jr., who's still a physics teacher. He's teaching in Dingwall. And Mr. Sharkey Sr. And this whole package was made up by Mr. Sharkey Sr., who's retired. And it never worked on Chromebooks, never worked on phones. But a colleague and I have been working on trying to get it onto Chromebooks. He's done the hard work. I was just helping him with the files. So you should be able to see two important files to be able to see. One is the theory, where you can play some animations and you click through notes. I've done some recordings of these before this website was up and running earlier in the year. I did some recordings using the website where I was doing some screen grabs, screen recordings, and posting them up, so you could see the theory. But this is where you can actually spend time yourself and you can do things. And I think it's quite good if you can do the experiments, because we're not in school to see the experiments. If we were, then you'd be able to see them. But this is a good a way as any to see them. Now, for the quantum waves, I think there's only about 3-4 possible experiments, the virtual experiments. One of them, which is this one you're looking at now, is the air wedge. You can probably see the air wedge thing at the bottom of the screen, the piece of paper propping up the microscope slides. And it doesn't really tell you anything about how to do the experiment. So this is one of them. The first one, I think, for quantum waves is stationary waves. Then there's this one with the air wedge. Then there's two different ways of using interference by division of wavefront. And I think there's a final experiment in quantum waves to do with polarization, which is the last section that we'll be looking at. But I thought we might have a look at this. Now, I'm not quite sure how this is going to work because I've got the simulation there. I also would need to go backwards and forwards, possibly to some theory, but this is the theory of the air wedge. Now, I don't know if anybody can remember off the top of their heads what the air wedge formula is. I mean, I can't remember all these formulae all the time. They are on the formula sheet. You do get a formula. Let me see. Could I pop back to my whiteboard and do a little bit of stuff on the whiteboard? I'm not quite sure. What can I do? I could stop presenting that and I could have a go at presenting my whiteboard instead, which looks like this, hopefully. Somebody will tell me my whiteboard's there, yes?
Yep.
Excellent. Okay. So really, I mean, there's a couple of things. There's some teaching to be done. There's the simulations to look at. And I just thought we'd have a look and I'd show you one of these simulations and you can have a play around with the rest of the program in your spare time. But the air wedge formula, now you're familiar with the air wedge because we've been looking at that over the last week or so. Here's two pits of glass seen from the side, propped up with something. Could be a piece of paper, could be a human hair, could be a bit of tin foil. It doesn't really matter. And the idea is that you can work out the thickness of this object that's propping up the two bits of glass. It's called an air wedge because there's air in it. You can put water in it. I think there were a couple of questions about what happens if you put water into this gap, what happens to the whole interference pattern thing. But certainly when I started teaching this, I think I did this a couple of weeks ago, and then I let you loose on one of Mr. Mackenzie's videos, which was not on this section, but on the section after it, which is young slits. This is interference by division of amplitude, and it's all this different reflections. So you get a reflection from here coming back up, you get another reflection from here coming back up, and then you have a look somehow at the interference pattern of these two reflections, and you use some maths, and you end up with a formula, and the formula is on the formula sheet. Delta x equals lambda L over 2D. So this is the air wedge formula. Now there is another formula, which if you've been following the Young's slits interference by division of wave front, there is another formula which looks a little bit similar, which is lambda equals delta x over times little d over big D, and they do look a little bit similar, especially if you rearrange this one and get lambda equals delta x times 2d divided by L. So there's a certain similarity, and you're going to have to just learn which one's which, because the chances are they're not going to tell you which one's which, and that's part of the plan, is that you need to learn them. So this is the wave front, this is Young's slits, and we did a formula about Young's slits. M lambda equals d sine theta at higher. But this is a reworked version of that, where you can do a little bit of maths, and if you've seen Mr. Mackenzie's video, you can make an approximation. There's what's called a small angle approximation for sine theta, which turns this formula, the higher formula, into, when you've rearranged it, if you put the n down there, it turns it into this advanced higher formula. So this is the wave front, interference by division of wave front formula, which is not what I'm just looking at the moment. This is the formula here for the air wedge, and you're just going to have to learn which formula applies for which. And there's a whole load of formula. You can't fail to have been impressed by the fact there's about 3 A4 pages of formulae for advanced higher, and you're just going to have to learn which ones are which. But that's the formula. So what means what there for the air wedge? And L is the length of the slide. That's L. You may see these in capitals, but this is L, the length of the slide here. Delta X is, when you look down here, you'll see the fringes, and they'll look like this when you look down vertically. Now they're very, very small, and you need a microscope. You need a special type of microscope called a traveling microscope. We have one in school in the physics department, and setting up the whole experiment and getting you to actually take some measurements is a bit of a performance, because the traveling microscope involves something called a vernier scale. Vernier was a French mathematician or physicist. I don't think there was a lot of difference between the two at the time. Vernier was somebody who invented a scale, a measuring scale for measuring very small distances. And we've got something, it's a microscope to make these look bigger. Obviously, that's what a microscope does. But the microscope actually has, when you look at it, you look down the eyepiece, it has something called some crosshairs on it, like a target. And then I'll draw these in a different color, but you then see the fringes like this through the microscope. And it's called a traveling microscope because you can actually move the eyepiece left and right, and you can position the eyepiece. That'll be a central bright fringe there. You can move the eyepiece left and right, and it's connected to this thing called a vernier scale. It's just like a ruler. It's a very, very accurate ruler measuring system, and you can position the crosshairs onto one of these fringes, and then you can take a measurement off the scale, and then you move the eyepiece, the microscope bit, you move it either to the left or right, and you go along a number of fringes. So you go along 10 fringes and you take another measurement, and then you take the two measurements away from each other, and it will tell you how far apart the fringes are. And it's a particularly tricky bit of equipment to use, but if there'd been any projects on the go this year, somebody would have done one of these, and I would have had to have gone through how to use the vernier scale, how to use the traveling microscope, and you can either measure the thickness of a bit of tin foil, or if you know the thickness of something you put in here, you can actually work out the wavelength of the light. So we've got the fringe separation, which we'll do in a minute, which is measured with this traveling microscope. So that's delta X is the separation. And then you've got this measurement here, D, which is how thick is the object you're sticking in there, the piece of paper or whatever it is, you can put in there. So that's the D here. You know what 2 is. Lambda is the wavelength of the light that you're going to use. I usually use monochromatic light of one color, monochromatic. So mono is 1 and chromatic is color. So one color. If it's one color out of Roy Gabiv, it's got one wavelength, and so it's got a particular wavelength for one color. If you use white light, you'll get a whole series of overlapping rainbow fringes, which I'm sure has been covered somewhere. Somebody will tell me if they can remember that, whether I've done it or Mr. Mackenzie does it in his video on Young's slits. You get overlapping colored fringes. There was certainly a little bit done about that at higher as well. So what can we use this equipment for? We can either use it for measuring the wavelength of light, or if you know the wavelength of light, you can use it for measuring D. So a rewrite of the formula, depending on whether you want to make lambda the subject of the formula or D the subject of the formula. So delta X, fringe separation carried out with the vernier scale. D, how thick the object is at the end. Lambda, the wavelength of light. So rewriting the formula, if you wanted to make D subject to the formula, must be this: D equals lambda L over 2 delta X. And that's what we're going to have a look at this morning with the virtual experiment, which is what you would see if you were actually in school, but you can only look at it one at a time. Here we can all look at it all at once. Okay, I see Finley's come along whilst I was doing all of that, so morning to Finley, to make another person. Right, okay, so what I suggest you do right now is get hold of a piece of paper, because I don't know who's making notes at the moment, but if you can get hold of a piece of paper, we're going to have a look using the software. Finley, you can talk to me since you've arrived. Everybody else was having a look at the announcement I posted this morning with a website address and a password to get you in either on your Chromebook or on your phone or anything else. Come to that that's got a web browser to get into two things, Finley: some notes, some presentation notes, called Virtual Flash Physics, and also to some virtual advanced higher experiments. And I will go back, because I don't think you were here with this, Finley, this morning when we started, but I'll go back and swap back to my virtual experiment screen. Are you all still with me at the moment? Just, I can't see you, but Callum, are you, just tell me, everything making sense so far, yeah? Yep. Thomas?
Yep.
Good. Susie?
Yeah.
Good. Mary?
Yep.
Good. Jamie?
Yep.
Finley, you've just arrived. You can check out that software later. I'm going to share the screen because I've got this on my Chromebook. I got it to work on my Chromebook, which hopefully you'll be able to do as well. I don't know if you've done that earlier today, but are you with me so far, Finley?
Yeah, I've got the website here.
Excellent. Is there anybody else? Who else is here? I can't remember who's here and who isn't. Callum, spoke to you, Finley, Jamie, Mary, Susie, Thomas. That's 6 of you. That's fine. That's good. Right, let's see if I can get back to the screen. That if you've got a phone, you could follow this on the phone at the same time as seeing it. Well, you're going to see me do it, but if you've got a second device, you might, and it's big enough, you might actually be able to do this. I'm not quite sure how well it would work on a phone, and I think you probably want to have a look on your actual Chromebook on another tab. You could always try opening it in another tab at the same time as I'm going through it. But what have we got here? I've got a sodium lamp. A sodium lamp, it's a bit like a street lamp, yellow, produces a yellow light. Some street lights I know produce white light, but a lot of street lights down the side streets tend to have these yellow lights. And again, we've got one of these in the department, and it produces this monochromatic light. So I ought to be able to turn it on and off, but it doesn't. It looks like I've turned it on and I can't turn it off at the moment. But what we've got here is does my cursor appear as well, moving around the screen? Somebody can tell me if the cursor's, the little arrow's moving. Is it moving?
Yeah. It is.
Yeah. Yeah, good. Okay, so I've got this light. The light's shining out of here, and it shines at this angled piece of glass here. This is called a beam splitter. What happens is the light comes along here and it reflects off this piece of glass. It's a see-through bit of glass, and it goes down here. And this is our air wedge. This is the propped up microscope slide sitting on a bigger flat microscope slide or a base with a piece of paper. So the light comes out of here, bounces, reflects off this, goes down, does the reflecting off the bottom of the top slide and the top of the bottom slide, and then the two beams of light where the interference happens here are reflected back up. And this is the clever bit, with this beam splitter, they don't reflect back this way. Well, if they do, we're not interested in that. They go back up through the bit of glass here and enter. This is the microscope up here. And so your eye would be right at the top here on the microscope. And this is the thing called the vernier scale. Okay. And it's in fact two very accurately made rulers, metal rulers. And you can see this has got a millimeter scale, and this one starts at 10, 11, 12, so on, 20, 30. But the vernier bit is this extra little scale here that is lined up with this bottom scale. So I'm going to call this the top vernier scale. I'm going to call this the bottom vernier scale. And the two scales, I won't go into quite exactly what it does, but the two scales, you can find websites that do simulations and tell you if you're interested. But the two scales enable you to read off a pretty accurate measurement, rather than just trying to what's called interpolate, rather than trying to measure where we are. in between any of these little scale readings. You use both the top scale and the bottom scale to get a reading. So this is what you would see. This is the yellow light with the black destructive interference fringes here and the yellow constructive interference there. Right, now what I think I can do is I can move the microscope. This is why it's called a traveling microscope. You move the microscope left and right to get the crosshairs, and there are in fact two crosshairs here. There's one going across there, and there's also one going down, which you can't see at the moment because it's lined up right in the middle of this destructive interference fringe. So what we want to do is to work out how to use the vernier scale. So I'm going to count here 10, 11, 12, 13, 14, 15, 16, 17. And I'm going to stop there because 17 is roughly what I think the reading is. And if I was to try and interpolate there, I'd probably say, well, it's somewhere between 17 and 18. Could be 17.3, could be something. How do I get a more accurate reading? Well, what we have to do is this top scale here is not at the same, quite at the same spacing as the spacing here. So this top scale is probably something like 0.9 of a millimeter spacing here, whereas this one is 1 whole millimeter. So what that means is because if this is 0.9 and this is 1, that the two sets of lines don't match up. And what I've got to do is find some pair of lines on the top scale and the bottom scale that actually line up with each other. So I've got to 17. Now I'm going to jump to my top scale and I'm going to see if I can find two lines that line up. Well, there's nothing with the naught there that lines up on the top scale with the bottom. There's a bit of a gap. If I move over here, I'm getting a little bit closer. That would be 17.1. Now, if I look at this one, these two lines appear to just about be lined up together, and that would be 0.2. So the reading here, where my crosshairs is 17.2. If I go across to the next one, which would be 17.3, I can see these two lines don't quite add up. And as I get further away, they definitely don't. So what I'm looking for is two lines, top scale and bottom scale, that line up. I've counted along here 10, 11, 12, 13, 14, 15, 16, 17 is my rough guess. And then I'm trying to find two lines, 17.0, 17.1, 17.2. And I'm going to say that my reading here accurately using the vernier scale is 17.2. Right, I would like you to write down that my crosshairs are positioned at 17.2 millimeters. Don't worry if you don't quite see what's going on here at the moment. 17.2. Okay. Now the traveling microscope will move along, and as it does, you'll see the crosshairs will move across the pattern here. And I think I've got to move it. If I move it to the left by clicking this button, I could move it to the right. It doesn't really matter, but I'm going to move it to the left, and you'll see. No, I'm going to move it to the right. I'm moving the crosshairs to the right, which means the pattern goes to the left. But you'll see the crosshair. Can you see the crosshair now has appeared? Okay, I'll move it back to where it was. 17.2 is my initial reading, and I'm going to move it to the right, and I'm going to count 10 fringes. Okay, so what I need you to do is look here, and this is on the 0 fringe. It's actually the M plus 0 because there's a whole load of other ones. And then I'm going to go to the M plus 1, M plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, plus 8, plus 9, plus 10. And I'm eventually going to get to this fringe with the crosshairs lined up. Okay, so I want you to count. All right, that's one fringe. Can you all see that I've moved one fringe? Anybody not see what I did there? If you're all okay, don't say anything. That's 1. And I think that's 2, 3, 4, 5, 6, 7, 8, 9. Now I'm on the 10th dark fringe along. The 10th dark fringe along. So I started at 17.2. Now I'm now going to take another reading from here to see where I've got to. Okay. And I've moved 10 fringes. So I'm going to count along here on my vernier scale. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I know I'm between 19 and 20. What exactly is the reading between 19 and 20? I need to move along the scales until I get 2 lines that line up, top scale and bottom scale. So no, it doesn't. No, it doesn't. No, it doesn't. No, no. And that one there looks like it's lined up. So it's 19.1, 2, 3, 4, 5, 6. 19.6 is my next reading. Okay, so I need you to write down 19.6. So I started at 17.2. And I'm just writing on my bit of paper here. I started at 17.2. I finished at 19.6. And that was for 10 fringes. Okay. Now what you need to do is take 17.2 away from 19.6. Somebody can do that for me and tell me what you get. Is anybody there?
2.4.
2.4, excellent. 2.4. Now that's 2.4 millimeters for 10 fringes. 2.4 millimeters for 10 fringes. Okay. I think what I'm going to do is I'm going to go back to my whiteboard here and we'll have a look. Now, what else information do we need? What other information do we need? Have we all got the formula written down that D is lambda L over 2 delta X? You should have started with that, or you should have started with delta X is lambda L over 2D. I'm going to go back to the whiteboard, but there are 2 other things we need to get, and I'll show you the formula again in a minute. L is 5 centimeters, so you need to record that L is 5 centimeters, and you also need to find out somewhere what the wavelength of sodium light is. Okay, so I want you to write down L is 5 centimeters. Now, whilst I go back to my whiteboard, I want somebody or all of you to go and do a bit of Googling and look up what the wavelength of sodium light actually is. Okay, so look up the wavelength, switch to a different device or a different tab and Google for the wavelength of sodium light, please. And I will go back to my whiteboard and we'll have a look at the calculations. And I'll hopefully stop that one, which was the tab. And I will now see if I can get back onto my whiteboard. Like so. Right. Okay, so I'm back to my whiteboard and you should be able to see that. So we've got, what we're actually going to try and find out is what was the thickness of the piece of paper using the theory that you've got. So what I've done is I've got the formula from the formula sheet. Delta X is lambda L over 2D. I've rewritten it in terms of D, and I've got D is lambda L over 2 delta X. Okay. So what have we got? What information have we got so far? We need to know what lambda is. We need to know what the wavelength of sodium light is. And hopefully somebody, more than one somebody, it would be great if at least one person has done it. We need to know what the wavelength of the light was, the sodium light that we're actually using. And you can just Google it and get an answer. Okay.
519 nanometers, sorry.
590.
Yeah, well, it's 589, but I mean...
Okay, all right. Well, we use 589 then. 589 nanometers. Okay, good. That's lambda. Now L on that experiment was 5 centimeters. 2 we know. Now delta X, we were on 17.2 is where we started. We moved the traveling microscope across to 19.6. So that means it's moved a distance of 2.4 millimeters for 10 fringes. So that means for one fringe, delta X is the fringe separation. Delta X, therefore, is 2.4 divided by 10. So delta X would be 0.24 millimeters. So I've now got all the measurements taken from the experiment. And there is a reason for doing this, because I have seen an experiment. Obviously, you don't get to move it. It's not an animation of it, but they do show you what it looks like, and they will probably have to give you this bit and that, and they'll tell you that it's 5 centimeters, and then you just got to put the numbers in. So what you need to do now is see if you can solve this formula, lambda L over 2 delta X. See if we can solve that formula. Everything needs to be put into meters. And then we'll get an answer for the thickness of our piece of paper in meters. So on your piece of paper, whilst you're sitting there scribbling, we need to do 589. Now 589 nanometers, what's that? Anybody know what that is in times 10 to the negative what?
9.
Yeah, okay, that's good. So we got 589 times 10 to the negative 9, our wavelength in meters. Now L is 5 centimeters, so I'm just going to put 5 times 10 to the negative. Anybody do centimeters? 10 to the negative. Somebody shout it out.
2.
2. Thank you very much. Good. On the bottom, we've got another 2. And we've got the 0.24 millimeters. 0.24 times 10 to the negative. Somebody shout it out. Come on, somebody shout out. Times 10 to the negative what for millimeters?
3.
3. Good. 3. Fine. So bung that. Hopefully you've got a calculator in front of you. I didn't say you had to bring a calculator this morning, but hopefully you've got a calculator, and you will then be able to work that out, and that will tell you the thickness of the piece of paper, having seen a virtual experiment. And you'll probably get something or other times 10 to the negative 5, I think. I'm not using my calculator. Somebody will get an answer for me.
6.14.
6.14. Does everybody agree with that? With Thomas? 6.14 times 10 to the negative 5 meters. Now there's 1,000 millimeters in a meter, because that's that conversion going that way. So if you multiply that by 1,000, you'll get a feel for how thick that piece of paper is, which I think is, we'll shift the decimal point, 0.061 millimeters for the thickness of the piece. I've got no idea whether that is realistic as the thickness of the piece of paper. Depends what the paper is. Paper comes in different thicknesses, but it seems about right to me. That if you stacked up, there's another way of doing this. Of course, you can just stack up, work out how many pieces of paper there are in a pack of photocopier paper and measure it with a ruler, and you'll get, I don't know how many sheets there are. Say there's 1,000 sheets in a pack, and you can measure it with a ruler and divide by 1,000, you get an answer. So that's another way of doing it. Right, okay. So I thought that would be worthwhile having a look at, because it shows you that the package is working. In other words, the virtual flash physics is working. You've managed to get it work. You can all see it. You can have a go at the experiment yourself if you wanted. You probably get some, if you started somewhere different on the vernier microscope scale, you'd get some different readings. You wouldn't necessarily start at 17.2 and go up to 19.6, but the 10 spacing should still give you about 0.23 millimeters. 0.2. I did it earlier. I got 0.24. So you'll get an answer which is pretty much the same for your fringe spacing. Moving the traveling microscope along, you've all seen that. So the main idea was that if you come across a question that says you're looking at air wedge fringes and you use a traveling microscope and the vernier scale says this, you would at least know exactly what's going on and you've got a knowledge of an experiment. And I think that's quite timely that I've been able to get hold of the access to the package. You can see the virtual experiment, and it ties in very nicely. We've only missed, believe it or not, one virtual experiment so far, which was to find the wavelength of a wave using stationary waves. So this was only experiment 2 of the whole of the quantum waves stuff. I mean, there's very few experiments you can do, to be honest, and they're all in this section. So I'd like you to go back and have a look at the virtual experiment before, stationary waves experiment. I'd like you to dip in and have a look and just show yourself that the other side of the virtual flash physics is working. Let me see if I can get that back for you. Let me go back to the experiment and then I'll swap out. So I want to go and see that. So you should be back at the experiment now, seeing that. What I want to do is go and have a look at if you're seeing the screen now, there's the experiments. There's the stationary wave one there, activity 1. To get these to work, that's a link to the experiment in blue. None of the rest of it actually works. So you can see the arrow changes to a hand, and that's the one we've just been looking at, activity 2. So you can have a look at that in your own time on the Chromebook. We've got a couple more which just tie in with the work we're doing at the moment. And then there's also, I've mentioned Newton's rings before to you, and we could have a look at that one later on. But what I really want to do is actually not just look at the experiments. So if I go back into the main bit of the program, this is where you should see, once you've logged in, try and save your password. So we've got the advanced higher experiments here. That's the things we've just been looking at. But there's also this separate section, just labeled plainly advanced higher. And if we have a look at that advanced higher section, if it's going to work, and it says it's wait for the player to load. And you might recognize this if you've been looking at my sort of notes that I post up. I do a lesson. Here's a video. Here's Mr. Mackenzie. Here's some what's called virtual flash stuff. Can we get this? If I right click here, I can get into full screen, so you can see the whole of the screen. It was in a sort of letterbox mode before, but you've got the whole course here. You've got Mr. Garrett's rotational motion and astrophysics, and has he just started astrophysics? It doesn't matter. You've got his electromagnetism bit. You've got my quantum waves, and you can just click through here and you can see all the different sections. And at the moment we're on this interference section, so you just use your mouse, or on your Chromebook you can click on the screen interference. We've got interference, division of amplitude, blah blah blah. You go clockwise round here. So these are all the sections that we've been doing, and you just come up with some notes. So if we look at I don't know, look at anything. This interference by division of wavefront, you'll get, hopefully, if it's working. Oh, now here we go. Takes a bit of time to load up, and you've got basically you've got a sort of interactive set of notes, and you can have a look. Interference can be also obtained by division of wavefront, because we've already done the division of amplitude. Use the arrows here to go through step by step. And as you go step by step, you'll see more notes appearing, or you can jump right to the end and see the whole page in a oneer, or you can go back to the previous menu, and it looks like it is taking a bit of time to do that. If it's because it's coming from a website somewhere. It's gone to sleep. I wonder if this will go forwards. This is going forwards easier. So interference, division of wavefront, and you can click on the play button and you'll get, there you go, two nice lots of waves diffracting at each slit and interfering, and you can do stuff. You can press buttons, reset. You can put on this thing called a trace, and then you can see where the lines overlap with constructive and destructive interference. I think it's quite good to have a look at that. The ones that I did, I actually did this, and I was screen grabbing. I was recording my presentation as I went along, and just clicking myself. But here you can stop, you can try the animations, you can go back yourself, you can go through the notes step by step. Can we use an extended source? No, you need a single source. You can get the information about extended sources and single sources and coherent light, and you can step through all of these and you get to see stuff which I hope is going to be useful for you, either to add to Mr. Mackenzie's videos, or probably more often now to mine, as we've done today. But I thought that would be useful for you. We've done just about an hour. I don't want to do any more now, apart from say, well, where should you be? And having seen, if you've watched it, Mr. Mackenzie's video last time, well, you should be around to this young slits and double slits, young slits with monochromatic light, young slits with white light, and getting the overlapping rainbow colors and some problems there. And that's the whole interference section done. And then if you look at this, this is where we started last year: quantum theory, particles from space and the solar wind, simple harmonic motion, then the whole section on waves. Every one of these, you can click on every one of these and expand it and add to your own knowledge. Interference, which if you've done the stuff I asked you to do before, is just about done. And then we've got this next section to move on to, which is called polarization. So familiarize yourself with what's going on here. Have a look, see if your notes are up to it. Use this stuff if it's useful. If it's not useful, don't bother. It's just another source of information. You've got Scholar, which has got some animations. You've got this stuff. You've got Campbell Robertson's notes. And we're just about there. I'm sorry we didn't get this working earlier in the year, but it's taken a long time to get this whole thing working and transferred across from PC to using interactively online via this new website that you've got the link to. Save the link. Your password should save somewhere, and we'll be moving on. And my plan is next week is to move on to polarization at the same time at 11:30 with me, if everything all goes well. And then that will be the last section. And I don't think this polarization, it's a fairly short section. You'll see here the number of bits to do is much less than in the whole interference thing, where you've got a whole range of stuff to look at. The polarization thing is much shorter. Now, I suppose the next thing is when are you going back to school? Just to finish off with. Nobody really knows what's going on. There is a date, March the 15th, I think it is. Whether it's going to be whole year groups or part year groups, I really don't know, but it certainly will involve 4th, 5th and 6th years. And of course, your 6th years, you will be asked to go back into school. Whether it is everybody goes back into school on the 15th or not, don't really know. Don't really know what's going on there. I have heard that social distancing needs to be maintained in schools, which isn't a problem with you lot because there's only 9 of you in the class, and having 9 in a class 2 meters apart is not a problem. It's a bit more difficult when there's 20 people, and if there's 30 people. I don't know whether the social distancing thing is being abandoned or not to get people back into schools. I haven't got a clue. Nobody seems to know what's going on, but I'm sure you will be back in school on the 15th. I think I should be back in school on the 15th. The good news from your point of view and my point of view is I have now been vaccinated, which should make me safer to be back in school. So I've got to sort out whether that's going to happen or not. You're the first people to hear about it. So I'll probably be back in as well. So we've got another, what's the date today? 1st of March. We've got next Monday as another video lesson, and then I may see you back in school after that. I think that's probably about it. Now, whether you've got any questions you want to ask me about anything, you can do so, because we said we're about an hour. If anybody wants to ask me anything about anything, do. Have you all got enough work to do? Have you got enough problems to work on? Have you got enough notes to work through? Enough videos to look at? Polarization next week. Anybody want to add anything? Callum, want to say anything? I'll just go through everybody.
No,
Okay,
I've got nothing.
that's fine. Finley?
I'm fine, thanks.
Yeah. Jamie?
I'm all good, thanks.
Good. Mary?
Yeah, I'm fine, thanks.
Good. Susie?
Yeah, all good.
And Thomas.
Yep, I'm good.
Good, excellent. Well, that's it for today then. If you think you haven't got enough to do, please send me an email. If I'm not being specific enough about what you need to do at the moment, please send me an email. If you want pointers towards particular pages and questions, come back to me. But you're all intelligent people. You should be able to find problems, plenty of Campbell Robertson problems to work through. There's Robert Gordon's problems to work through. Play around with the virtual flash physics. Go online to Scholar. Anything else you like to do this week and next Monday, 11:30 polarization, hopefully. And that's it. And I'll say goodbye for today. And thank you very much for turning up.
Thank you, sir.
Thanks, sir.
That's okay.
Cheers.
Thank you very much.